Start, and I will give you a quick going through about how to utilize the Dshape algorithm to analyze some real data. And today I will focus on analyzing the trans-abdominal maternal ECG signal. So this is the trans-abdominal fetal maternal ECG. That is the ECG lead that is put on a pregnant woman's abdomen, and the recorded ECG signal will contain both maternal ECG and the fetal ECG. So if you go to the lecture I gave before about Dshape, you can see a overall introduction about this data set and what we want to do. So like before, in the very beginning, we will clear all the parameters and close all the figures, and then load the necessary toolboxes. And the Dshape, that is the main folder for the Dshape algorithm. And then we will load the real data, real signal. And the data is from this CINC 2013 database, which is publicly online, freely online, that you can get easily. And we will use case 5 to demonstrate the overall algorithm and what you will get. And in this database, the main feature is it contains experts labels about fetal ECG peaks. So you load it. You load the data, and you load experts labels, and so on. And today I will demonstrate how to apply the Dshape on 2 different channels, because this database actually contains 4 different channels, and we will focus on channel 2 and the channel 5. And we start with channel 2. Okay, and the sampling rate is 1000 hertz. Record data is the parameter, the variable for the recorded data. And then we run some very basic pre-processing, removing artifacts, and so on. And you will see what I meant by artifacts later if we encounter some. And then we run some basic pre-processing and remove trend using median filter and so on. So this is a median filter. We use 0.1 second length median filter, which is roughly, although it's very median filter is a nonlinear one, so you cannot really say what it is related to the frequency domain, but it's roughly 0.1 hertz. Oh, okay, and sorry, 0.1, 0.1 second. Okay, so it's not about. So sorry. Anyways, it's not about spectrum. This is kind of, it's very nonlinear. Okay, and then you remove the trend and so on. And then sometimes you may need to remove the power line interference in etc. Okay, and then you may run some extra steps to detect R peaks directly from the maternal trans-abdominal maternal ECG. And then you use the detected R peaks to evaluate the instantaneous heart rate by doing the interpolation. And if you do not know what it means by the definition, what does it mean by instantaneous heart rate? It simply means how fast your heartbeat per cycle per second, or even every quarter second, and so on. And we can also use the ground truth fetal to get the ground truth fetal instantaneous heart rate using experts label. Okay, if you and you can go to the previous lectures about how to define instantaneous heart rate. Then we plot signals for visualization. Okay, so let's do it and stop here. And you will see what's going on. And let's take a look at the signal. Very good. So that is what we get. I gave you 4 different plots. This is the first plot. As I mentioned, there will be 4 channels in the data, and in the recorded data matrix, there will be 5 columns. The first column is time, and from column 2 to column 5, that will be the first 2 fourth channels. Then what you can see is, well, this is a typical ECG signal. You can see that is a P, this is R, right? And you can see T, and so on. And there are some kind of, well, may look like artifacts. And if we zoom in, then you may see something clear. For example, here, you see this is R, right? And you have Q, R, S, and there is kind of like T. Very good. And but in addition to that, you see this is clear, right? There seems to have some kind of smaller jump, smaller bit, smaller, like, well, looks like artifacts. But turns out those small peaks, they are fetal ECG. They are the ECG associated with the fetus. And you can take a look at other channels. You can see, hey, look, well, it's more difficult to identify which one is which because the fetal ECG becomes larger here. And if you go here, then you see, oh, well, this is wider, so which is maternal ECG, okay, because PQRST and heart rate are somehow nonlinearly related. And this is fetal heart rate, fetal ECG, which seems to beat faster. Okay, very good. So we have a very basic observation of the signal. In short, the trans-abdominal maternal ECG is a summation of 2 ECG signals. One is from mother, one is from fetus. And the mother ECG, because mother is an adult, so the heart is larger. Although the ECG lead is put in the abdomen, you can still collect a very strong ECG signal from the mother. But because of the projection direction of the dipole current modeling your electrophysiological dynamics, sometimes you may see that the fetal ECG might have similar strengths like maternal ECG, like the height are the same. Okay, then what we do is this is second figure, right? And this second figure is, in this case, the same as the first one because there is no artifacts. Okay, very good. So we don't see anything fishy here. Then third one, this is the detrend signal. That is, what is trend? If you look at here, you see, well, there is some kind of fluctuation, right? I told you those peaks are maternal ECG and those peaks are fetal ECG. But what about those kind of, you see, there's some kind of going up, going down, going up, going down, going up, going down, right? And here as well, going down, going up, going down, da 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 da, da 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 da, and here, da 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 da. Well, that is trend. And we apply the median filter to get the trend removed. And as I mentioned here, in the code, this kind of detrending is very, very specific. It's not universal at all. Actually, detrend itself is a very, very difficult topic. And usually it depends on application. And this way, we use this short time median filter that is very, very specifically applied for our purpose in trans-abdominal maternal ECG analysis. It is not universal. For other data sets, for other biomedical signals, you need to determine the trend based on the feature, based on the database. Okay, but anyways, this is what you get after detrending. Now, finally, I zoom in. Yes, here. I just zoom in. Okay, 4 channels, and I zoom in, and I superimpose the circles. Those circles are the detected maternal R peaks by running traditional R peak detection algorithm, which you can see, oh, quite nice, isn't it? You can get most of the maternal ECG, and those red crosses are fetal R peaks that are provided by experts. Okay, so our mission right now is, can we decompose maternal ECG and the fetal ECG? Or if we can recover maternal ECG and the fetal ECG, that is the ultimate goal. Or would it be possible to just estimate fetal heart rate or fetal R peaks? Either way, ultimately, we want to do a decomposition so that we can get a full information about maternal ECG and the fetal ECG. If we cannot, can we estimate fetal heart rate and so on? Okay, and you will see that the Dshape algorithm will be one way to help us to achieve this goal. In particular, when we only have one channel, one ECG, one trans-abdominal maternal ECG channel. Okay. Now let's remove the figures and continue. Next step, once we have now observed the data, now the next step is let's run Dshape and see what we get. And why Dshape? If you remember, that is because maternal ECG and the fetal ECG, they are both non-sinusoidal, oscillatory, and so on. So if we do not use Dshape, but just use traditional short-time Fourier transform or synchrosqueezing, then you will get just junk, a lot of junk. Although it's not that they are not useful, but it will be very challenging to do the interpretation. So let's run it. Okay, I set all the parameters. This is the same as before when we played with the simulated data. And then we run the Dshape algorithm. That is exactly the same as before. The main difference is here there is a more specific paper that we focus on to do fetal ECG extraction on single-lead abdominal ECG by Dshape algorithm and so on. Okay, and today we will only talk about the Dshape part, and in the next lecture we will talk about non-local median or manifold learning scene. Okay, so let's run it. Let's see. Oh, it's done. Okay, good. And if you pay attention here, it is quick because I somehow downsample the signal to 100 hertz. There is no specific reason here, but simply to speed up the computation. Why? Because we only need to get a rough fetal ECG information, rough fetal ECG heart rate information. So we don't need it to be so too fast. Okay, but certainly you can run the algorithm without downsampling. Okay, but that is you can play with it yourself. Finally, let's observe the result and see what we get from the Dshape. Very good. So this is a plot. First, if you pay attention, you will see, oh, this is not too bad, isn't it? Short-time Fourier transform, synchrosqueezing, you see, 1, 2 harmonics, right? Because the signal oscillates non-sinusoidally, so it's expected to get harmonics, and there is a fast varying instantaneous frequency. So when your frequency increases, the instantaneous frequency changes becomes fast, so that you get spectral interference. We have discussed all these kind of things before, so we know what's going on. Synchrosqueezing certainly cannot help in this case. You still get a lot of junk. Anyways, then you run Dshape. The Dshape short-time Fourier transform suddenly give you only one component. All the harmonics are gone. Okay, and the Dshape somehow enhanced the concentration of the final result. Okay, looks good. But you may ask, look, Hao-Ting, this looks a bit weird, quite weird, because we know there are two components. One is maternal ECG, one is fetal ECG. But you now tell me there is only one component. What's going on? What's going on? Well, the answer is very simple, because fetal ECG is relatively weak in this case. So if you pay attention and read very carefully, you can see there is actually something very much like a curve here. Very much like a curve here. But it's hard to really convince yourself to say there is something. But if you, well, maybe, right? But after synchrosqueezing, no, you don't see anything, right? Zunyin, no. It's hard to say. Fine. Now let's see. I just superimpose the so-called ground truth. The blue line is the fetal heart rate that is provided by expert's label. The red curve is the maternal heart rate that comes from detecting maternal ECG's peaks. So you can see, they fit quite well. Okay, so this case, well, good. But you don't really get much fetal ECG. That is a bit weird, isn't it? Okay, so we get a first conclusion, that is, there does exist fetal ECG, but somehow in the time frequency representation, it seems to be already kind of, kind of masked, or have been kind of, masked by maternal ECG, because maternal ECG is too strong. So what can we do? Okay, short answer, FYI, is that we need to decompose the signal first. Okay, and how to decompose the signal, as I mentioned, we will need some manifold learning stuffs and so on that we will cover next time. So right now, you don't see anything. Okay, well, very bad, very sad, but that is fine. For this kind of application, that is nature. So our next step will be trying to remove the maternal ECG. But how? One thing you may say is, okay, well, we have learned something, right? Because from here, right? Now, from the Dshape short-time Fourier transform, we can get maternal maternal heart rate. And once we get maternal heart rate, right, then we can come back to the synchrosqueezing transform or short-time Fourier transform to recover the fundamental component of maternal ECG. And then once we get the phase and amplitude modulation, then we can just apply like what we did before by applying, this is here. We can just apply SEMT, but I don't do it here. Why not? There's a reason, and you can play with it yourself, because SEMT doesn't work in this case. Okay, and there is a reason for it, and that is why we need manifold learning algorithms, non-local median, etc. Okay, good. So now we have seen this channel, second channel, but well, technically it's first channel because this channel is 2, but well, this is 2, but means first channel. I should say first channel or lead. Okay, so this is fourth channel. Lead. Now, in this case, as you remember, I showed you before, the maternal strength and the fetal strength will somehow be similar. So let's see what we get. And this time, let's run everything at once, and then we can take a look together. Okay, so run. Okay, very good. So now let's take another look. This is the first channel that we observed before. In this case, you see, although we can see the fetal ECG, but it is relatively weak. That is why you don't see too much. But in this channel, the magic is, well, not really magic, but fetal ECG is stronger, much stronger. Okay. So that, well, you can get something, it is kind of more challenging to just use height criteria or some basic ideas. Well, you need to do some, well, spatial filtering and so on, so that you can get the fetal, the maternal heartbeats correctly. But you can see that, well, it's maybe not so useful. You get some fails. But well, this case is still very good. Oh, okay, fine. So you can still get very good maternal R peak detection just from force channel. Let me double check. See if well. Let's see. So this is okay. I already used the force channel. Okay, well, fine. Then this is a very good case. So, anyways, you get very nice R peak spec and so on. Now let's see what you get from the Dshape. This time, you can see. Hey, hold on. This is weird. I have changed to, sorry, I forgot to change to 5. No wonder. Sorry, that is weird. Okay, so let me rerun it. Okay, very good. So now, now this looks better, much like what we expected. So now I detect maternal R peaks using this channel. Then you see there will be start to have some kind of erroneous detection, although it is not super strong. You can still see how the heart rate is not too bad, but it is already kind of slightly wrong that you need to do some modification. Okay, and now if you look at the time frequency representation, you start to see, hey, there is a very strong component here that you can even identify and with, well, kind of a visually confidence that there's something here as well. And if you run Dshape, oh, look, it is kind of much cleaner that you can say there are really two components. And there is a very important question related to this kind of argument. I say, hey, look, there seems to be something, right? But how confident you can say there is really something? That is something we call uncertainty quantification, and I will find some time to discuss that issue. But anyways, you see two components, and if you superimpose the ground truth, the blue one is the ground truth, then you see, hey, that superimposed with this high frequency component very well, isn't it? Which tells you that we can, from this picture, obtain fetal heart rate information in this case. But as I told you, in most cases, sorry, fetal ECG is too weak, so you may not be able to see too clear information about its heart rate. And then, furthermore, if you take a look at these R peaks, this maternal instantaneous heart rate, you see there are some kind of small jumps, small bumpy jumps, which suggests that the R peaks detection is not very well. But in this case, as I mentioned, well, it is still, the maternal ECG is still relatively good, relatively good, strong, so that you don't have too much trouble getting the maternal instantaneous heart rate or maternal R peaks. But in some other cases, which you can play with, you can find some cases in the database that the fetal ECG is stronger, so that if you just apply the traditional peak detection, then sorry, you don't get the desired result. Okay, so this is another case. So that is what you can apply, and the Dshape algorithm to help you to get the maternal R peaks. And then the next step, will be peak tracking to determine, okay, where are the correct R peaks and so on. And then you use that correct R peaks and so on to decompose, reduce the impact of maternal ECG and get to the remaining part. And from there, you can get fetal ECG and so on. And that will be the next part of the lecture. Okay, and so I think that is pretty much about how to utilize Dshape in real database. And we will continue next time with how to remove the maternal ECG and get fetal ECG, even get fetal heart rate, and that will be the manifold learning part. Okay, that will be the next part. Okay, so